I really hope these two look different and not white for everyone. What's that? Oh, right. Yeah, that's the question.
Okay, so let's continue there with the Nima Hoda, part 2, systolic and quadratic topics. Please take it away.
So, yeah, okay. So we're going to take a sharp turn today, although it's not that sharp of a turn, as we'll see a bit later, into a new classes of non-positively curved complexes, which have a kind of stronger local combinatorial nature to them. So I'll start by defining triangle and square complexes. A triangle complex, respectively, square complex is a two complex whose two cells are, well, triangles, respectively, squares. Let's get an idea by looking at a pair of examples. Okay, so there's a triangle complex. And here we have a square complex. Those square complexes are two-dimensional cubical complexes. So you've been attending Nir's talk. Okay. Now, let D be a disk diagram or Van Kampen diagram. When D is a triangle complex, respectively square complex, it is cat 0. So you've heard about cat 0 cubical complexes. In the case of a square complex, well, that's the same definition. For triangle complexes, well, for disk diagrams that are triangle complexes, it's when its interior vertices, or at least this is an equivalent condition, when its interior vertices have degree greater than or equal to 6. And if you remember your link condition from Nir's course, then the square version of that is greater than or equal to 4. Okay. So these complexes that I drew before are actually also disk diagrams. So we see that neither of them is cat 0. For example, here we have an interior vertex of degree 4. But if we didn't have that, let's say if this was our complex, or let's say if, here's a better way to do it. If instead of that 4 wheel we had this, then okay, now we have a cat 0 triangle complex.
I assume you're like factorizing each triangle like a Euclidean triangle.
Yeah. I mean, although in truth, what I'm doing is I'm ignoring metrics and thinking of this purely in combinatorial terms. So that's, but yeah, if you metrize them as Euclidean triangles here, regular Euclidean triangles of side length 1 and regular Euclidean squares of side length 1, then cat zeroness coincides with exactly this for disk diagrams. So yeah. And over here, we're not cat zero as a square complex disk diagram because we have a vertex here of degree 2 and a vertex here of degree 3. But suppose instead we had something like that. Okay, now it's fixed, right? And here, suppose we actually could replace this with a single square. Okay, now we're cat zero. Okay, right? Okay. Okay. Let's get our main definition here. A triangle complex, square complex, X is locally systolic locally quadric if any minimal area this diagram D to X is cat zero. Okay, and we'll see that this is actually a local definition in a moment by giving an equivalent characterization. So this diagram is a combinatorial map from this diagram into X. So this diagram in X. And this minimal area, if it has the least number of 2 cells among all disk diagrams for the same boundary cycle. Does everyone understand this, the definition or what's being said here? Okay, so why is this a local condition? Here's a proposition. It's not too hard to check. X is locally systolic local if any this diagram D in X of a form to the left below can be replaced by one of a form to its right. Okay, I haven't said anything, but I'm going to give a bunch of sort of local replacement rules that ensure that our complex is locally systolic or locally quadric. Okay. And for the pentagon, so the idea is that anytime you have a vertex of positive curvature, one that has degree lower than it should be, then you can replace that whole bit with a disk diagram having this, for the same boundary cycle, which has no interior vertices and then necessarily lesser area. course, there's some number of ways of triangulating a polygon. So, well, I won't write them all. So that's in the case of systolic complexes.
One only has one interior, does it?
The first one should have no interior vertices because, and keep in mind that the replacement should have the same boundary length. Yes, thank you. Yes. Otherwise, those are squares. So that's the definition of locally systolic or locally quadric complexes. Well, the local characterization. Okay, and it's not hard to see why anything satisfying these rules is locally systolic or has cat zero disk diagrams. Because I mean, if your disk diagram is not cat zero, it's going to have a sub disk diagram essentially that has one of these pathologies in it, and then you can replace it with one that doesn't. There's less two cells in the replacement diagram that you've performed the surgery on, and so the process must eventually stop, and then you get something that's cat zero.
Question?
Yeah.
So how come the ones on the left, like near the bottom, why are those not cat zero? Like square with the vertex in the middle?
This one?
Yeah.
Okay, so for disk diagrams, you are cat zero for triangle complex disk diagrams. You're cat zero if every interior vertex has degree at least 6. And this vertex is an interior vertex of degree 4.
Point is, use that as cat zero, but that's not the metric.
That's right. That's right. So yeah, that's exactly the point. Your disk diagrams, you can find ones that are cat zero, but that doesn't at all mean that your complex as a whole is going to be cat zero because, well, you have these kinds of pathologies, right? We just know how to replace them. I'm not going to use this board because green does not work on that board. All right. So that's what the local definitions are. Now, a systolic, respectively, quadric complex is a locally systolic, respectively, quadric complex that is simply connected. Okay, so sort of by definition, we have a kind of local to global theorem. And a systolic, respectively, quadric group is one acting properly and co-compactly on a systolic, respectively, quadric complex. So yeah, and we're going to see that these are really two sister families of complexes, even though they have their differences. They behave in much the same ways, and the techniques that can be used on them are very similar. So some attribution. Where did all this come from? Well, number of places. I mean, these things were sort of invented and and reinvented multiple times. Chapoy and Sultan, they studied bridge graphs, which are essentially the same objects. Yanish, Gavich, and Montkovsky reintroduced them and into the world, or redefine them with higher skeletons and in the context of geometric group theory, as did Haglund. I was independently. The quadric complexes introduced as hereditary modular graphs, as far as I understand, by Bandelts. And then I glued squares to them, my master's thesis. And then this kind of point of view and is due to Wise, this kind of disk diagram replacement type. PQ complexes. So this is in a preprint of Donnie's. These are both examples of what he calls generalized PQ complexes. Already erasing colored chalk. Right. Okay. How about examples? Well, cat zero complexes. Those are cat zero, triangle, square complexes are systolic, and quadric. And I'll just say that you know what a cat zero square complex is, a triangle complex. It's cat zero if it's vertex links. Sorry, locally. Cat zero if its vertex links have girth at least 6. Okay, so just how near defined links do the same with a triangle complex. And to have girth at least 6 means that the shortest simple cycle in a link has length at least 6. Okay, you'll notice that that's, yeah.
So when we metrize a triangle complex, do we sort of take the triangles to be equilateral? Is that why I need to have 6?
Yeah, that's yeah. So this is the same as the local to global condition for cat zero spaces. So this is exactly the condition. If you metrize them as Euclidean equilateral triangles of side length 1, then this is exactly the condition you need for the links to be cat 1. So yeah. Okay. More examples. Ballman and Bryn, for any n, or not so much more examples, but these are examples of cat zero triangle and square complexes. In fact, they do it general polygonal complexes. For any n, if L is a finite regular graph, finite connected regular graph of large enough girth, then we can obtain simply connected fact, contractible n-gon complexes with vertex links, all isomorphic to L. In fact, they show that you can get uncountably many. We've also got right-angled Artin groups and right-angled Coxeter groups with triangle-free defining graphs. You can check that those are all two-dimensional cat zero square complexes, or that they act on them. C4 T4 groups is a method to turn a C4 simply connected C4 T4 complex into a quadric complex. Ballman and Frankowski give a group theoretic version of this Ballman-Bryn construction. If L is a Cayley graph of a finite group of girth at least 6, they are able to obtain a co-compact simply connected triangle complex with links isomorphic to L. Okay, so that actually gives groups. Wise showed that C6 T3 groups are systolic. C3 T6 groups are also systolic. That's sort of known and not too hard to prove, but apparently not written down anywhere. A2 tilde buildings are systolic. And just so we know that we're getting really new things here with these quadric and systolic complexes, Januszkiewicz and Frankowski, they produce examples of torsion-free hyperbolic systolic groups of arbitrarily high virtual cohomological dimension. So what that means is that these groups are not just things acting properly and co-compactly on two-dimensional cat zero complexes. So, okay, any questions until now?
It's okay if you don't know the answer whether we're going to like the systole, like usually when I think of a systole, I think of like a shortest curve or something. Is there a relationship between systolic complexes and this, or?
Yes, yeah. So if you think about those replacement rules, so let's say you have something like that. Now, if you look in the link, you have of this vertex, you have a square, which is a cycle, and the replacement rules tell you so you either have this or you have this, and the replacement, and so there's kind of like these guys and these guys, like these two guys along with this form a triangle. Okay, that triangle is there in the complex. Same as these two guys and this guy. And so telling you that you have this replacement is essentially telling you that in the link there's this square has a diagonal. So that's the connection. That's why it's called that. Yeah, it's not a
What is the square having that in the diagonal, like the link square having that in the diagonal,
Mhm.
like, what's the relationship between that and shortest curve?
right. The relationship is that I think the link is not completely
So then the number of edges, so pause is small.
Okay.
Maybe,
Okay, I'll be satisfied with that.
all right.
High-dimensional quadric.
I believe that I know how to do that. Yeah, it's not. I was using similar ideas as yeah. Yes.
In the case of a reg and a constant group, is the ring complex and the constant complex is scalic or a quadric? In that case, is that the complex that they have?
I think if you just take the Cayley graph and you glue in squares where you see 4 cycles, you're gonna get so yeah, so that's probably the same as one of the complexes that you're talking about. Okay. So I mentioned that these things were seen in the graph theory world, and so let's talk about the metric graph theory of systolic and quadric complexes. Yeah, okay, so it turns out that a cat 0 triangle or square complex say disk diagram here has isometrically embedded boundary path if and only if D is either just equal to a triangle in the case in the triangle complex case, and in the square complex case, D is equal to a square. Okay, and Nir's given us the tools to see why that's true. If you have a square complex this diagram, its boundary is going to be isometrically embedded if and only if, whenever you take 2 antipodes, the 2 paths you have on the boundary between them are geodesics. And that's going to happen if and only if you don't pass through the same hyperplane twice, right, on one side or the other. So what that means is if the boundary is isometrically embedded, then our hyperplanes should always be going between antipodal pairs of boundary edges. Okay, so we don't have. On the other hand, we should not have any more than 2 pairwise crossing hyperplanes, right? If you had 3 pairwise crossing hyperplanes, right? So you had some pairs of antipodal, you had 3 pairs of boundary edges corresponding to hyperplanes, and they all pairs crossed, then there would have to be a cube here, right? So, but this is a square complex, it's 2-dimensional, there's no cube. So that can't happen. So if you think about it, you'll see that the only possible way that the hyperplanes can interact is, well, let me draw it that way, is that way. And that corresponds exactly to the disk diagram being a single square. So that's okay. So we actually have the following theorem of Chapoy for systolic complexes and myself for quadric complexes, that the one skeletons of yes, a grid larger than a single square. Good question. The question is, what goes wrong with the grid? The, n by n grid, I guess. So what goes wrong is this, right? So I can find a pair of non-antipodal edges that have a that are the ends of a hyperplane. So what that means is that there are a pair of antipodal vertices of the boundary cycle that cross it twice. So then that's not a geodesic. And the bound, I mean, that's what does it mean for the boundary cycle to be isometrically embedded? Yeah. Other questions about that argument? It's been a while since I've thought about that argument, but there's a way to prove something even stronger that sort of reduces to the square case in a way that I don't fully remember. But what actually happens is that in these cases, the boundary cycles are not just not isometrically embedded. If they're long enough, then there's a pair of antipodes that are closer by a constant, uniform constant fraction with respect to the distance in the cycle. And if you check my paper on shortcut graphs and groups, I give an argument. There's a way to turn a two-dimensional systolic complex into a two-dimensional quadric complex. And so there is a way to do it that way. And there's probably other better ways to do that, but yeah. I think there may be a way to get hyperplanes from cat zero triangle complex in the plane, but yeah, I don't remember quite exactly how that goes. So yeah. Other questions? Yeah. So let me finish the statement of this theorem, which is going to tell us that essentially these objects are characterized by their one skeletons. So it's, these are really in some sense they're graphs of systolic, quadric complexes are precisely the graphs for which any isometrically embedded cycle C to X has length C equals 3 in the case of quadric, and C equals 4. Sorry, C equals 3 in the case of systolic and C equals 4 in the case of quadric. Okay, and given that one skeleton in the graph, you can actually recover the complex as well. So we see that this is this goes two ways. We can recover X. We can recover a systolic quadric complex from its one skeleton by gluing in a unique triangle or square to each embedded cycle of the right length, 3-cycle, 4-cycle. Okay, let's continue on to dismantleability. Talk about asphericity and contractibility of these things. Okay. Yeah. Let gamma be a locally finite graph without loops or multi-edges. And gamma is not empty. Gamma is not equal to a single vertex. A vertex V of gamma is dominated or bidominated in gamma if there is a vertex W, what I call it, W not equal to V in gamma such that every, say, other sorry, in the one case, in the dominated case, we want a neighboring vertex such that every other vertex neighbor of V is adjacent to W. Okay, somehow W is friends with all of these friends. What does that look like? We have V here. Those are all of V's friends. Here's W. He's got all of those guys as friends, and maybe he's got some more friends. And that's where the rest of the graph is. And you know, in the for dominated, we also want W to be a neighbor of V. Otherwise, we don't. This is sort of, you wouldn't have that in a bipartite graph, and you should think of this bidominated as being a bipartite version of this. So, okay, how does this help us? What does this have to do with contractibility? Well, we say that gamma, we're going to give a kind of combinatorial version of contractibility. Gamma is dismantleable, bidismantleable. There is an enumeration of its vertices, B1, B2, B3, such that Vi is dominated in the full subgraph of gamma induced on the This is the prefix graph. This is the graph on the vertices from V1 to VI. We don't care about the guys that are bigger than VI, right? We just want VI to be dominated in this prefix. For every I greater than or equal to 3. And oh, sure. Yeah. All right, we need both versions here. So dominated by dominated. And also ask that V1 and V2 be adjacent. Okay. So let's look at examples of dismantlings. Here's a graph, and here's a dismantling order 1, 2, 3. So 1 and 2 are adjacent. In the prefix, 3's neighbors are 1 and 2, and 1 is also a neighbor to 2. So he dominates 3. Here, 4 has neighbors 3 and 2, so either 3 and 2 dominate. 5 has neighbors 3 and 4, so either of those guys dominate him. 6 has neighbor 5, who is also a neighbor of 3, so 3 dominates 6. And then 7 is dominated by 4 and 3 here. Okay. And now an example of a bi-dismantling. It's a bit small, maybe. So we can start in the middle. 1, 2, 3. 3 is dominated by 1. 4 is dominated by 2. Okay, 2 has the same neighbors as 4 does. 5 is dominated by 3. Okay, because 3 has 4 as a neighbor and 4 is 5's only neighbor. 6 is dominated by 4. 7 here is dominated by 4. 8 is dominated by 1 and also 5. 9 has 1, right? Yeah, we're good. 9 has neighbors 8 and 1. This is dominated by 7, which has those as neighbors. 10 is dominated by 1 because his neighbors are 9 and 2, and 1 has those same neighbors. And 11 is dominated by 8, 1, and 10. Okay, so that's a dismantling order. Okay.
For the left one, which vertex dominates the 3?
Which vertex dominates 3? Keep in mind that 3 is not dominated in the entire graph. Okay, 3 is not. What you need is that 3 is dominated in the prefix. The prefix is the graph on 1, 2, and 3. Yeah, so he's dominated by both 1 and 2 in the prefix. That's a very important point. Yeah, thank you. Okay, how much time do I have? I think 3. Didn't we start a bit late? I want to have a little bit. Okay, thank you. All right, good. Okay, so why is this relevant to us as or why is this relevant to geometric group theory? Well, written that one in this color. Well, it turns out that you can upgrade a dismantling you can upgrade dismantleability to contractibility. Okay, if you have the right kinds of cells. The flag simplicial or bisimplicial completion of a locally finite, yeah, of a locally finite dismantleable, my dismantleable graph is contractible. Okay, now I won't say what exactly that is. The flag, well, I won't fully say it for the bisimplicial case, but in the simplicial case, it just means, well, I think we got a definition, but it just means that anytime you see the one skeleton of a simplex, which is a complete graph, a finite complete graph, then there's a unique simplex there. So we just glue in all the places where we can add simplices. That's how we get the flag completion. In the bisimplicial case, there's a family of cells whose one skeletons are complete bipartite graphs. These are non-polyhedra. Maybe I'll just draw a few of them. Squares are bisimplices. And then the first sort of the first interesting bisimplex is this one. So that's the bisimplex on K23. You can see it's, if you put in the squares, you get a sphere, and then you can plug it and get a ball. And in general, inductively, you can glue in all the lower dimensional bisimplices to a complete bipartite graph, and then pray that it's a sphere, and then plug it with a ball, and that's how you construct bisimplices.
In the square diagram there, I don't see how why is 5 dominated in the subgraph? Which vertex is dominated by?
3.
I thought every neighbor of 3 had to be adjacent to 5.
It's that every neighbor of 5 has to be adjacent to 3 in the prefix graph. Yeah. Okay. Oops, where did I go? All right, so let me just finish by stating a theorem and a corollary. Theorem. There's Anstey and Farber. In the finite case, extended by Chapoy to locally finite. I guess maybe not explicitly, but the argument is the same. And then Bandelt for the quadric case, the one skeletons of locally finite systolic quadric complexes are dismantleable by dismantleable. Okay, and as a corollary, flag completions are contractible, and the torsion-free systolic quadric groups have finite KG. Okay, and there are other kinds of results about these groups and complexes of a non-positive curvature nature. There are flat torus theorems, axis theorems, fixed point theorems for finite groups acting. But yeah, I'll stop there.
Anything special about triangles and squares, but you generalize this to like bigger polygons.
I think there is something special about triangles and squares. So yeah, I mean, for bigger polygons, in order for the disk diagrams to be cat 0, if they're regular Euclidean side length 1 that's how you're viewing them, then the vertex degrees would have to be at least 3. That's already negative curvature. So that's already puts you into the hyperbolic world necessarily, if you try to directly translate what we're doing here. So I guess that's one way to answer that question. Another way to answer it is John McCammond and a student of his studied cat zero. Sorry,
Michael Doherty?
I don't remember.
Oh.
Yeah. Yeah. Sorry for that. John, yeah. They have a paper. I don't know if it was published, but there's a preprint where they study cat zero triangle square complexes, and there's lots of interesting phenomenon that can appear. Like there are many different ways of tessellating the plane, for example, using triangles and squares in a cat zero way. So, and that's not the kind of behavior that you see in systolic and quadric complexes. So I think already, yeah. So that's another way to answer that question. But also, you can try to push things in those directions. Yeah, that would be interesting, I think. Yeah. Yes.
Maybe you said that right. If you have a torsion, you actually know how.
If you have a torsion-free one, well, how is the group given to you? I guess that's the. Do you have the the quotient of its action on a quadric or systolic complex? Yeah, if you're torsion-free and systolic, then the action is free, right? So you do have this quotient, and yeah, you can perform the flag completion on the quotient, even if it's not like a even if the cells are no longer embedded, and right. So what you look for is the right kinds of maps from complete graphs or complete bipartite graphs into your complex, and then you glue in the right kinds of cells, simplices or bisimplices.
Like if you have an infinite group that acts with bounded orbits, for instance, you get a fixed cell point for.
So yeah, the version that I know, and I think there are more general things proved, by Polat in this systolic case, but the version that I know is that if you have a finite group acting on a quadric or systolic complex, let me say locally finite just to be safe, then it stabilizes a clique or a bisimplex. Yeah, and that's something that follows. That's a dismantleability. Yeah. I mean, it's quite. I mean, in the case of a finite, graph, and well, I'm not claiming that in general. I don't know, but I'm only claiming this for quadric and systolic. But for a finite dismantleable or bidismantleable graph, it's that condition is true in general. And essentially the way it works is you look at all the dominated vertices. That's invariant, and so all the non-dominated vertices are also invariant, and you can remove those, and now you have a smaller problem, and it's by induction you wind up getting a invariant clique or biclique.